This comes out of section 4.2, max min values. First one gives me this function, f of x equals 4 minus x squared, defined only from 0 to 2, including 0, not including 2, and it says find any max min on this graph. So first of all, I need to know what the graph looks like. We have ourselves a parabola facing down, 1, 2, 3, 4, it's been moved up 4 units if we think of it in terms of transformations. We have a point here, and we have a curve facing down, but we have an open dot here because of the fact that it doesn't equal 2. And we don't have to draw any of the rest of this because this is the only part given this restricted domain here. So looking at that picture, we can see that there's an absolute max, which is also a local max, of course, but an absolute max at 0, 4. The maximum value of this function is 4. It never goes any higher than that. And even if we drew the whole parabola, that would still be the case. This graph has no minimum value. Because of the fact that it's got an open dot there at 2, 0, 2, 0 is not a point on this graph, and you can go as close to 2 as you want to. You could go 1.99, 1.99999, 1.9999999, you know, as many 9s as you want to put there, and get infinitely close to that point but never touch it. So you can't say what the minimum is because there is no minimum to this one. Now let's look at a kind of a similar example. This time we're given a cubic polynomial, f of x equals x cubed minus 3x, and told only to draw it from x being greater or equal to negative root 3. Now it's a strange number to pick, but it's not accidental that it's actually the x-intercept here. So we have ourselves a graph that looks something like this, and we have some points here. This one is negative 1 comma 2, this is negative root 3 comma 0, this is 1 negative 2, and this is root 3 comma 0. And as far as finding max min is concerned, we have a few things to look at. We have an absolute min, absolute minimum at the point 1, negative 2, because this graph never goes below that. The lowest value of this graph, or of this function, is negative 2. We have a local minimum as well at the point negative root 3 comma 0. That point is lower than all points surrounding it, because as you move away from it, you have to go up. You have a local max at the point negative 1 comma 2. It's not absolute because of this part of this graph. This part of this graph that is increasing infinitely to the right means there is no absolute max, that this graph would go up and up and up as high as you wanted to draw it. And so we have an absolute min, a local min, and a local max looking at that function. So it brings me to a very important idea here, and it's called Fermat's theorem. It says that if f of x has a local max or min at c, then one of two things must be true. Let's look at all the max or min points that we've seen so far, even if you just look at the ones on the graphs on this page. The only place where you might have a local max or min is either the first derivative is equal to 0, or the first derivative does not exist. Because if it does not exist, you can have all kinds of weird things going on, like points, you know, like on the absolute value function where you have places like that. You can have curves like this where the first derivative is 0, or you can have endpoints where you can't do a derivative, so the derivative is undefined. But that's the only place you're going to have max or min, local max min, is at places like that. You would not have, you know, if the first derivative is positive, your graph must be increasing. So you can't have, you know, for instance, here or here or here a max or a min, because if the graph is increasing, by definition that means that the graph is going up through that point, so there are points lower and points higher around it. Same thing true if the first derivative is negative. If the first derivative is negative, it would be decreasing, so it would be going down somewhere on this graph, and we couldn't have a max or a min there either. So Fermat's theorem is kind of interesting. These values, these points C, where the derivative is undefined or zero are called critical numbers. And so there'll be lots of examples coming up where we'll be asked to find the critical numbers for a certain function, and basically all we have to do is find when is its derivative 0 or when is it undefined.